All right, here is the next example, and this one right here is a classic calculus problem. So we definitely want to make sure we know how to do it. We have a rectangular plot of land that has a river on one side, like that. These two values will be the same because it's a rectangle. We have 1,000 meters of wire. What are the dimensions of the largest area that we can enclose? This is a great problem. We want to make the area of this field as large as possible, but we know that we only have 1,000 meters of wire to work with. All right, so with a problem like this, it always helps to draw a picture, and I always recommend that you do that. Next, it's come up with your objective function and come up with your constraints. And be aware there may be more than one constraint. So our objective function, I'll just call it G, is we want to maximize area, and so that's going to be the width times the length, W times L. So we know that W times L is the function that we're trying to make as big as possible so that we can capture as much area as possible for our cattle or whatever we're grazing or whatever. What is our constraint? Well, we know that we only have 1,000 total meters of wire, and so that means that W plus L has to equal 1,000. All right, so W plus L has to equal 1,000 because notice we don't put fence along the river, so it's just width, length, width. That's going to equal our perimeter. Also, if you wanted to, you could put down that both of those values will need to be bigger than 0 because it doesn't make sense to have negative fence. All right, so that means our constraint is 2W plus L equals 1,000. And now you're ready to go. I went through that pretty quickly because I've had a lot of practice with these. Oftentimes the hardest part of these problems is just coming up with these two equations. And so again, just try to actively think, what are you trying to maximize or minimize? And what are your constraints if you have them, including these over here? Once we have these pieces, the pattern is the same. Solve for one of your constraints. So I'm going to solve for L. L is going to equal 1,000 minus 2W because we subtract the 2W to the other side. Once you have that, take your constraint and plug it into your objective function. So our objective function is now G is equal to W times replace L with 1,000 minus 2W, just like that. This is great because now we have an equation with just one variable. So this will be G equals 1,000W minus 2W squared. And once we have that, we can take the derivative. So G prime is going to equal 1,000 minus 4W. There's our derivative. And now we can solve it by setting it equal to 0 because that's when the relative minimum or relative maximum will happen. Add 4W over, we get 4W equals 1,000. Divide by 4, divide by 4, W equals 250. We should also check the constraints of 0 and 0, but if we did, we wouldn't have a field, so we're okay on checking the constraints. I mean our endpoints. I went through that kind of quickly, so if you need to rewatch this, that's understandable. Once we have our W, we can easily find out what our L is by just plugging it into our constraint. So our constraint was 2W plus L equals 1,000. The 250 can go in for W. And so we get 500 plus L is equal to 1,000. Subtract the 500 over, and you get L is equal to 500. So the maximum that this field can be is if we have a width of 250 and a length of 500. And you can find out what the area would be by just plugging those into the objective function. So if we grab our calculator, we can do 250 times 500 and get 125,000. So square meters, because we're talking about area. So when you do a length of 500 and a width of 250, we get 125,000 square meters of field, and that is the most you can get. If you make any adjustments to these 250 or 500s, you'll get a little bit less than this. Now real quickly, let's see why that is. Look at what our function was that we took the derivative of. Notice that it's an upside down quadratic. So if I just put the width along here, Obviously, if I have a width of 0, we get 0 area. And if I have a width of 1,000, we have 0 area. So we have 0 and 1,000. And we know that this is going to be an upside down parabola because it's negative 2w squared. So, it's going to look something like this. And the value that's going to maximize our area is going to occur at the vertex of this, and that happens when it's 250 for the width. And so that's the idea. If we put the length on here, it would have been 500. So that's the idea right there. Hopefully it's making sense. We'll do one more example, and then we're actually going to be done with this section.